Hello, class. Dr. Foley again. This is going to be the other major part of Chapter 1, which will deal with the numbers part of science. So you got to know some vocabulary. That's what I've been discussing in the last 90 minutes or so. In the next hour to 90 minutes, what I'd like to cover with you are how do we express all these measurements. You have to know some of the units and the metric system versus the English system we'll talk a lot about. We tried to introduce the metric system in this country when I was a kid. It just never took off. We're so used to thinking in yards and miles per hour and ounces and things like that. But in this class, you're going to have to think in mass and grams, not pounds. You're going to have to think about length in centimeters and meters and not feet and yards, and so on. So it's much more, the metric system is a much more useful system for scientific things because it's based on powers of 10. So it's not covered in your chapter, but you need to know how to express and understand things in scientific notation. So I want to just review that before moving on. This is in Appendix B of your online textbook as well. So when you have a number written in scientific notation, it looks something like this. It's at some number A, and A is always going to be a number between or less than 10. That's the standard way to write it. It would be anywhere from, let's say, 1 to 9.99. And then you express where the decimal place is by moving it with a power of 10. So that's all you're doing when you're multiplying by a power of 10. You're either moving the decimal place to the right or you're moving it to the left. Why do we do this? Because in science, especially chemistry and physics, we have to express either really large numbers, like if we're talking about how many molecules or atoms there are in a sample, or we have to talk about really small numbers if we're talking about the sizes of atoms and molecules. So this class is difficult for some because you're trying to you're learning about things that you can't see. Atoms and molecules can't be seen with our eyes. So again, the convention is to write the number as a number between 1.00 and 9.99, depending on how many significant figures you're going to express your number with. And then you just multiply by a power of 10. So let me just give you some examples. So the number 10,000, if it's just written as 10,000 without a decimal place, we'll cover this in a little bit, that will tell you how you should write it in scientific notation. If it isn't written with a decimal place, you just assume that you have to write the number 1 and then tell me where the true decimal place is. So this is where you imagine the decimal place to be here. Let me just put a little X there. And then the decimal place is really here for the number 10,000. So you have to count 1, 2, let me just draw that with little arrows. 1, 2, 3, 4 places to get to the true decimal place. So I moved it 4 decimal places to the right. So therefore, I multiply it by a power of 10 to the 4th, because 10 to the 4th is 10,000. 10 times 10 times 10 times 10 is the number 10,000. If you're trying to express a really small number, this isn't terribly small, but it's small. This is the number 1. So you imagine the decimal place would be here. And now you have to tell me that the number is small. So we have to multiply by a power of 10 that's less than 1, because when the power of 10 is less than 1, you're actually moving the decimal to the left. So 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, 10 to the negative 4th gets me to the true decimal place. So that's why this number 0.0001 is also expressed as 1 times 10 to the negative 4th. So you have to remember that for a really large number, this power of 10 will be a really large number. And for a small number, the power of 10 will be a number less than 0. I should probably say that's a number less than 0. So let me edit that there. That should be less than 0. It's a negative number. And this should be a number greater than 0. All right, so let me just give you some more examples. For instance, the speed of light is 186,000 miles per second. If we want to write that in scientific notation, again, the true decimal place for this number is here. We imagine it to be here because we want to write the number as a number between 1 and 10 multiplied by a power of 10. So the only place I can put the decimal is here between the 1 and the 8. So it's 1.86. And then I count 1, 2, 3, 4, 5 places to the right. Therefore, this is a power of 10 greater than 0, so it's 10 to the 5th. The number 250 million people, for instance, would be a very large number. So the power of 10 will be greater than 0. So you imagine it to be here, and you count 1, 2, 3, 4, 5, 6, 7, 8. 10 to the 8th. This is the same as this number. And you also have to be able to enter these in your calculator. I'll show you how to do that on this particular model. I think you can be able to see that. Let me put it in standard mode here. So for instance, if you wanted to enter in 186,000, the normal way, it's very easy, just 1860. That's pretty obvious. How do I express that in scientific notation on this calculator? And whatever calculator you do have, it's going to probably be a similar process. On mine, it's just the second function, and then the 5 key, and then it puts it into scientific notation. There it is, 1.86, and then a superscript 05. Your calculator is not, at least this model, is not going to show you scientific notation like this. It's not going to show you the actual number 10 to the 5th. That's expressed in a calculator with this little raised 05. It has two digits in it because you might have a power of 10 that's greater than 10. And then it stays in that mode. So let me turn it off again. Let's try 250 million. So if I type in 250, there's 250,000, 250 million. So then I put second 5, 2.5 to the 8th power. You can see how easy that is in a calculator. Why is it second 5 on my calculator? Because it's hard. You probably can't see it on my calculator, but the other function of this key is, it says SCI. That stands for scientific notation. And it's the other function of this key. So that's why I pressed the second function. So you have to figure out on your calculator how to do that. I believe this EE key will also do that. So let me try that. Let's see if I put 2.5 and then I type in EE. You'll probably see a little 00 pop up. Then I can put 8. So that's another way to directly enter scientific notation. If I wanted to enter in this number here, a really small number, 2.5 times 10 to the negative 11th, I could enter then. I could do it this way, 2.5 EE minus 11. Now, if I say equals, it's not going to change it to a standard number because my calculator display doesn't have enough decimal places. But if I did it for this number, it might do that. I'll show you. So I can enter in, make sure I'm in the camera shot, 2.5 EE8. Now, if I hit equal, you see it changes it to 250 million. If I want to go back to scientific notation with my model here, I just go second 5. So you can see whatever calculator you do have, then you need to be comfortable with using the expressing numbers with scientific notation. The other way we say scientific notation is exponential notation. So this number here, this really small number, is 2.5 to the negative 11th power because you have to count 11 places to the left to go from where you want the decimal place to be to where it really is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I move to the left, therefore my power of 10 is less than 0, so it's 10 to the negative 11th. So that's a quick review of scientific notation, also called exponential notation. Make sure that you are comfortable with that. So let's go back to our sheet here. and just review what I hope to accomplish with you in this next few videos that I'm going to probably splice into one long video. We're going to explain the process of measurement, identify the three basic parts of a quantity, describe the properties and units of length, mass, volume, density, time, temperature, and practice some calculations with what's called unit conversions. That's a really useful skill that you're going to use throughout the entire course. So measurements provide the information that we need. That's the basis of most of the hypotheses, theories, and laws in chemistry. So let's go to the next sheet here. So what am I saying here? I'm saying every measurement provides three basic kinds of information: the size and magnitude of a number, a standard of comparison, that's the unit, and an indication of the uncertainty. So we express this uncertainty using sig figs. So what you saw in those other, that previous slide or that previous page were significant digits, significant figures. This number has 3, this number has 2, that number has 2. And I'm going to review that with you in this video. So let's talk a little bit about these units, okay? What tells us that the number that I'm saying is what it is. If I just said 250, why are units important? Well, if I said 250 million what? Atoms, people, $250 million, you have to put a unit on there. This really small number, without the unit m, meters, is meaningless. That's why units are just as important as the number part. So make sure you always write the units in your calculations so that we're not confused by what you're trying to say. Without units, a number is meaningless. So if you're driving 100 miles an hour, do you mean 100 miles per hour or 100 kilometers per hour? In chemistry, we use an updated version of the metric system. It's called the International System of Units, or SI units. It's from French, System International. So that's where SI comes from. It's used since 1964, and there's a chart in your book, I think it's, or table 1.2. It gives you these, what are called the base units of the SI system. There's 7 of them. We're going to ignore the ones dealing with electric current, so that's why I have this crossed out here, which is amps. But this isn't a physics class, so we don't really have a use for that. The other one that we're not going to really worry about is the unit of luminous intensity, how bright an object is, which is the unit called candelas. But we are going to deal a lot with 5 of the units. The unit of meter is the length, the standard unit of length. And the symbol that you want to use is a lowercase m, like that. So be very careful when you write units. Do it exactly as I'm saying here, because this is standardized. We all use this language. The other base unit is mass. How much stuff is in a compound or in a sample. The name of the base unit is a kilogram. You might have heard that word before. That just means 1,000 grams. So we express that with a lowercase k, g, like that. Time is useful. That's another base unit. The base unit, or the name of the base unit, we're all familiar with. So this is the one unit that we've all used: seconds, minutes, hours, days, years. But the standard unit, the base unit, is seconds. What do I mean again by base unit? The base unit is just whenever you express any of these things, you're going to use this base unit and then just use a prefix in front of it to tell me what it is. Except for mass, we generally are going to use the gram and just say, is it a kilogram, a milligram, or whatever. The Kelvin is telling us how hot or cold an object is. So temperature is a reflection of how fast the atoms in a sample are moving. It's a measure of the energy of a sample. And so we're not using degrees Celsius or degrees Fahrenheit. We're using a capital K, which is called a Kelvin. Now, we do sometimes use degrees Celsius There will be times when I use degrees Celsius, but many times I'll have to use Kelvin. And there's a very good reason why. I want you to maybe think about why would we want to invent this temperature scale of Kelvin. There's a very good reason for that. Now, the other thing that's important is how much stuff we have, the amount of substance. That unit is called a mole. All right, it's not an animal. It's like saying a dozen. And the symbol of the unit is just the word without the letter E on it. We couldn't use little lowercase m for mole because it often is the first letter or first couple letters or a couple letters from the name. But m was already taken with mass, so we had to use MOL. Now we express the relative sizes of these base units, whether they're really large, there's a lot of them or a very few of them, with prefixes. Fractional or multiple SI units are measured with a prefix or expressed with a prefix. So the most important ones that you should learn or get comfortable with are from small to large are called femto, and they're not capitalized. Pico, nano. You might have heard of nanotechnology. That comes from the metric prefix nano. Micro, milli, and these go about, what I'm doing is going every 3 decimal places, I'm getting a 1 unit larger, 1 prefix larger, except here. That a centi is just 1/10 or 10 times bigger than that. Deci, which is 1/10. And then the really large ones, kilo, mega. You might have heard megahertz frequency, or giga. We're familiar with these terms because they express the speed of a computer many times. So the question is, how do we express these as powers of 10? That's what we want to do. How do we express these as powers of 10? Sorry, I'm still getting used to this camera, and some of my paper might be out of the camera shot for a few seconds, so I'll get used to this. It's a new camera a new phone that I'm using for this. So how do we do this? Let's look at this chart. This is table 1.3, kind of partially filled in. Where can I put this here? Right about here is good. Let's fill in the missing cells together. So again, what does femto mean? Well, now these metric prefixes that I just mentioned, the common ones, these have abbreviations. We don't want to always have to write out those words. We want an abbreviation of these prefixes to put on the abbreviation of a unit. So this is like learning a new language, Spanish, French, whatever. You're learning the basic words of the grammar of scientific subjects. So femto is a lowercase f 10 to the negative 15. So pico, P-I-C-O, is a lowercase p 10 to the negative 12. Nano is you might imagine, then would be a lowercase n, and that's equal to 10 to the negative 9th, 1 billionth of something. And then we have micro. Now, micro is not a English letter. It's a Greek letter. It looks like this. It's called mu, and I'll put it in quotes, M-U. That's how we say it, mu. And it's written, I just write it kind of like this. I think you should be able to see that. You kind of go, it looks like a U with a little leading curl to it. That's the proper way to write out the letter mu. And that means 10 to the negative 6. That's 1 millionth of something. And then we have, now we're getting into the realm of things you're probably more familiar with. Milli, M-I-L-L-I, means, is the prefix lowercase m. Now this is not mass, it's for milli. So some letters, we only have so many letters, we have to use, they have a double purpose. So the context of how we use the letter lowercase m is important. Does it mean mass or does it mean milli? Well, it'll be obvious to you when you're looking at certain numbers. Centi, like centimeters, is lowercase c. That's 1/100th of something, 10 to the negative 2. Deci, D-E-C-I, is the lowercase d. That's 1/10. Again, you should be comfortable with writing them numbers like this, powers of 10, or writing them in standard notation. So 10, for instance, 10 to the negative 3 could be written as 0.001. 10 to the negative 2 could be written as 0.01. Notice that when the number is really small, that the number of zeros is always one less than the power. So 10 to the negative 3 has 2 zeros. 10 to the negative 2 has 1 zero before you write the 1. 10 to the negative 1 would be a tenth, 0.1, and so on. Some of the larger units are kilo again, as I mentioned. That's a lowercase k, and that's equal to 1,000 of anything, a kilometer, which we say is a kilometer. Mega, M-E-G-A. The abbreviated symbol for that is a capital M, and that means a million something. Again, 10 to the 6th is just another way to write a million. So it's a 1,000,000,000. Now, if this is review for some of you, just be patient. This is going to be useful. So we need to make sure everybody's on board with this. Giga is a capital G. That's a billion of something. And tera, like a terabyte computer, is a capital T, and that's a trillion of anything, 10 to the 12th. So now let's go on to some of the more specific units, like I mentioned, the base units. Let's talk about length a little bit. How do we use length in chemistry, and how do we express things this way? So again, the SI unit of length is the meter. And it was originally intended to be 1/10,000,000th of the distance from the North Pole to the equator. So you can see these units and are just man-made inventions. They are totally made up. We could have said the meter is anything, but they chose it to be 1/10,000,000th of the distance from the North Pole to the equator. Why'd they do that? I have no idea. But that is not a reliable standard to base the meter off of. What we've done over the decades and centuries of developing these things is that we've come up with ways to base units on things that never change. So for the meter, a meter is defined as the distance light travels in a vacuum, because the speed of light in outer space doesn't change. That's what I mean in a vacuum. It never changes. So it travels at approximately 186,000 miles per second. But if you actually converted this fraction to that, it would probably be a little bit more precise than 186,000. Why don't you, if you want a good exercise in unit conversion, figure that out. If it's going at 186,000 miles per second, then how long does it take to travel 1 meter? That would be a good exercise for you. And maybe I'll try that later on in the video and show you how that's done. But it's 1/299,792,458. All right. So we know that a meter is a very small unit relative to the speed of light. A meter is about 3 inches longer than a yard. So a meter is defined as 100 centimeters. And how do I know that? Because I know that a centi is 1/100th of anything. So it takes 100 centimeters to make 1 meter. And it's about 39.4 inches. An inch is an inch is considered exactly 2.54 centimeters. So here's figure 123 from your book. And so some of the relative distances. A meter is just a little bit longer than a yard. And a centimeter, 100 of these little centimeters would fit inside of a meter. So an inch is 2.54 centimeters, and so on. Those are just relative lengths. These aren't obviously the actual lengths of these things. But that's a useful conversion to use. I'm hoping that looks like it's in the camera shot. All right, so moving on here. Let me just show you some of the extremes of length in science that go from really small to really large. So for instance, the reason why it's helpful to express things in scientific notation is if we're looking at a hydrogen atom, the diameter of a hydrogen atom is 2.4 times 10 to the minus 10th. If we had to write that in standard notation, that would be equal to, you'd have to write it like this: a 0.12345678924 lowercase m. You see, that's not really convenient to write. Let me make sure that's done right. 2.4 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the standard notation of this. So atoms are incredibly small, if I do the mental math right, if there's about 240 billion atoms per meter, there's hundreds of millions of meters in a centimeter. So atoms are incredibly small. That's why we need to use scientific notation. The circumference of the Earth is about 24,900 miles, or 40 million meters. But on the grand scheme of everything, that's tiny, tiny, tiny. If you look at this diagram here I found in another textbook I used to use, it shows you relative scales. It's hard for us to imagine like how far the moon is away even, or how far the sun is away. What does that really mean compared to us? Well, astronomers have done the mental, not the mental math, but the actual calculations for us. Just to the nearest star from Earth, it's 25, how do I read that number? 25,000 million, billion, 25 trillion miles. That's a long way. Or it can be in the metric system, that would be 39 trillion 900 billion, I think, million, thousand, million, yeah, 39 trillion 900 billion kilometers. What does that really mean to us? How does that work? Well, relative scales sometimes help. So imagine that the sun were the size of a tennis ball. If we shrunk everything down and the sun were the size of a tennis ball, about like this, then the Earth would be smaller than a grain of sand. But where would the grain of sand be relative to the sun and the nearest star, Alpha Centauri? Well, if the sun was no bigger than this tennis ball, it would be 19 feet away from us. So 19, 20 feet away, and we're the size, smaller than a grain of sand. That's actually how far the Earth is from the sun. The Alpha Centauri, one of the closest stars to the Earth, would be 890 miles away from us. So light travels at about 186,282 miles per second. It takes 8 minutes and 20 seconds for a ray of light to leave the sun and reach the Earth. So really, when you're looking at the sun or the nearest star, you're actually looking a little bit into the past. The sun, when you see the sun, it's actually 8 minutes ago when that light left the sun. If you look at the nearest star, it took 4 years for that light to get here. And the light's traveling at 186,000 miles per second. So that gives you an idea of how huge the universe is. And so we think the Earth is large, but relative to this sort of distances, it's really nothing. All right, moving on to our next base unit, which is mass. That's how much stuff something contains. The SI unit, our base unit of mass, is a kilogram, kg. A kilogram is about 1,000, or not about, it's exactly 1,000 grams. Now, originally the kilogram was defined as the mass of a liter of water. A liter of water is a little more than a quart. But that wasn't a reliable enough standard to use for mass. So they came up with an actual piece of metal. I think this is the only base unit that's based on an actual object. The rest are based on natural phenomenon of some sort, speed of light or frequency of an atom's vibration, something like that. This is based on an actual object, and it's made out of platinum and iridium. And it's very stable. It's an alloy. It's kept under a vacuum. This is the replica that's kept in Maryland, but the original is kept in France, where the SI system offices are. A kilogram is about 2.2 pounds. So if you expressed your weight in kilograms, you'd actually weigh, I weigh about 185 pounds. So I would weigh about 84 kilos, they say, 84 kilograms. So you have to get used to thinking of mass or weight in kilograms or grams. A gram is about the size of a sugar cube, if you want to get a grasp of what a gram is. But again, this is a standard, so it means we have to base all our units on something that we all agree upon is what a kilogram or second or whatever whatever the unit we're talking about is. The other base unit we use a lot in chemistry is temperature. It's how hot or cold an object is. It's a measure of the kinetic energy of the particles. So the SI unit of temperature is the Kelvin, as I mentioned earlier. Now there's no degree symbol on a Kelvin. So if room temperature, RT, is about 298 Kelvin. We write it like that. And that's about equal to 25 degrees C, which is about equal to 72 degrees Fahrenheit, something like that. That'll give you an idea of the relative difference between room temperature and Kelvin. Looks like a really hot temperature, but the Kelvin scale is based on a freezing point, or absolute zero, so it's a rather large looking number. The degree Celsius is also used in the SI system, so we will use degrees Celsius a lot as well. Now, the nice thing about Celsius, degrees Celsius and Kelvin, is that they're exactly equal. The only difference between the two is where the zero is placed on the scale. Water freezes at about 273.15 Kelvin, which is 0 degrees C, and water boils at 373.15 Kelvin, or 100 degrees C. So there's the difference between a Kelvin and a degree C is a difference of about 273 degrees. The coldest possible temperature that's not okay, that's 0 Kelvin. Again, we don't say 0 degrees Kelvin, we just say 0 Kelvin. And that's absolute zero is negative 273 degrees Celsius. That's the coldest theoretical temperature we've been able to measure. We've gotten very close to that in our laboratories, but we can't quite reach it because in theory, all molecular motion is supposed to stop at absolute zero. Just to give you an idea of the relative differences of temperatures, liquid nitrogen, the boiling point of liquid nitrogen, you can imagine, is pretty cold. It's negative 196 degrees C, which on the Kelvin scale, if you add 273.15 to that, I won't always be picky if you use the 0.15, but it's 273 that you add to Kelvin to get to, or that you add to degrees C to get to Kelvin. The temperature of interstellar space, you can imagine, is really cold too because there's nothing out there. So if there's no atoms in interstellar space, there's no energy really. The energy is really low, so it's negative 270 degrees C. It's almost just barely above absolute zero. How is that? What is that on our Fahrenheit scale that we can kind of understand? It's negative 458 degrees Fahrenheit. Can't even imagine how cold that is. But there's a limit on how low the temperature can go, but there's no limit on how high the temperature can go. A lightning strike is 50,000 degrees Fahrenheit. The air actually heats up with lightning strikes, so you're actually seeing the air glow white hot. The surface of the sun is 5,778 Kelvin. That's not even as hot as sorry about my sloppy writing there. I'll maybe go to a finer tip pen. 5,778 Kelvin. The core of the sun, incredibly hot, that's 15 million degrees Celsius. Really hot. That's so hot that it actually causes the temperature of that actually causes the atoms to fuse together. So this is what's going on in stars. It causes nuclear fusion. That temperature is so high that hydrogen atoms, two hydrogen atoms combine, to give you a helium atom plus heat or light. That's where sunlight comes from. It's fusing hydrogen atoms into helium and releasing the excess energy as heat. And the other unit that's important to us is time, of course. We use it in chemistry. When we talk about how fast chemical reactions occur, we talk about time. Now, a second is defined or standardized in this way. I got this off the internet. It's a little hard to understand. I'll try to explain it. In 1967, this committee adopted the second to be the duration of a huge number of periods of the radiation corresponding to the transition between two hyperfine levels of cesium atom. What does that mean? It means that this cesium atom is the electrons transition very regularly and are very stable. So you can cause electrons to move around in atoms if you give them enough energy. And that's a very regular, repeatable phenomenon. So that's why they use that particular atom as the standard for what a second is. So that's pretty obscure, but we use it because it never changes. So we want our standard of what we're basing our unit on to be something that never changes. Just like the speed of light out in a vacuum in outer space never changes. That's why we base the unit of length on that. Some of the extremes of mass that you come across in scientific endeavors are why we want to, again, use scientific notation is because atoms are incredibly small, incredibly light. So an atom of gold, for instance, we think of gold as being a heavy, dense metal, which it is, but the mass of one atom is 3.3 times 10 to the negative 22 grams. That's 21 zeros in front of the number 33. A mosquito weighs 2 milligrams, or about 0.002 grams. An elephant weighs 5 million grams, or 5,000 kilograms. The Earth, believe it or not, we can actually calculate the mass of the Earth is a huge number, as you would predict, 6 to the power of 24 kilograms, which would look like this. So again, we're going from the really small to the really large in science. So we want to be very comfortable with using scientific notation. So going back to time, smaller and larger time intervals can be expressed with appropriate prefixes. I should have probably shown you that other thing on mass a little earlier because I was talking about time, but that doesn't matter. So we also have these units besides just mass, length, excuse me, time. We have these units called derived units. And the two most important derived units that we use are volume and density. What is a derived unit? It is a unit that's combining two of the base units. So volume is the amount of space that an object takes up. It's length times width times height. Let me try to use a darker pen for this. It's length times width times height. We live in 3 dimensions, 3D. So we need to have 3 dimensions for volume. So the SI unit, the standard unit for length, of course, is meter. So if you take a meter times a meter times a meter, you get what's called a cubic meter, which we write as lowercase m with a power of 3. Other useful units for volume are the liter and the milliliter. So a liter is defined as a cubic decimeter, and a milliliter is exactly equal to a cubic centimeter. So to help you understand why that is or where that comes from, this is going to be incredibly useful to you, actually. The fact that 1 cubic centimeter is equal to 1 milliliter. So imagine that you have a cubic meter. A cubic meter is like the size of a trunk of a car. It's pretty big. If you take 1/1000th of that and take it out, this little cube, you have what's called a decimeter. A decimeter is 1/10 of a meter. So a decimeter would look like a cube. Let me draw a cube here. from the, if we're looking at a cube on the side, a decimeter, 1 decimeter cubed would be equal to 10 centimeters here, 10 centimeters here, and 10 centimeters here. Again, let me stress where that comes from. Deci, the prefix DECI, means 1/10 of a meter. So 1/10 of a meter, if a meter is 100 centimeters, 1/10 of 100 is 10. That's where this 10 comes from. 1 decimeter is 10 centimeters. But if we're cubing it in 3 dimensions, length, width, and height, or length, width, and height, however you want to look at it, it doesn't really matter. It's 3 dimensions. You'd have a cube that looks like this. So if you multiply that out, 1 cubic decimeter equals 10 times 10 times 10, or 10 to the cubed centimeters cubed, which is equal to 1,000 cubic centimeters. We define that as a liter. So instead of saying a cubic decimeter, they invented this word called a liter, which is spelled L-I-T-E-R, but we use capital letter L. If you go to the supermarket and buy soda pop or anything in liquid form, you'll see the unit of liter or milliliter on these labels as well. But because because there's 1,000 cubic centimeters in 1 cubic decimeter, that's where we come up with the fact that 1 cubic centimeter is therefore equal to 1 milliliter. Let me say that again because it's important. If you take a liter, which is 1,000 cubic centimeters, and divide it up into 1,000 pieces, you will have one cubic centimeter, which is 1,000th of a liter, or 1 milliliter. So these are interchangeable units. In the first lab that you're going to do, where you're calculating the density of an egg, this will be very helpful to you. The other important derived quantity is what's called density. The density of a substance is the ratio of the mass of a sample of the substance to its volume. So it's mass divided by volume, or D equals M over V. Sometimes you'll write it like this: D equals lowercase m over capital V, like that. When I type things out, I have to do it like this in horizontal fashion, like that, so /. But it really, if you're going to write it properly, you would write it as a fraction like that. Now in the standard, the SI system, this standardized system that they invented in Europe, the standard unit is a kilogram per cubic meter. So going back to our definitions earlier, density is an intensive property. But it's based on 2 properties that are extensive. So the amount of stuff, mass, and volume, how much space in 3 dimensions something takes up, depend on the amount of material. Those are extensive properties. But it's interesting, if you take the ratio of 2 extensive properties, you get an intensive property. What is an intensive property again? It's a property of matter that doesn't depend on how much of that stuff that you have. So again, the density of my gold ring will be the same as the density of a chunk of gold that's the size of a football. It's an inherent quality of gold, or whatever element or compound you're talking about. But in the SI system, since kilogram is our standard unit of mass, and the cubic meter is the standard unit of volume, then you get kilograms per cubic meter for the SI unit for density. That isn't really convenient for us, a kilogram per cubic meter. In chemistry, we deal with much smaller sizes of matter. So on the milliliter size, which is, again, a milliliter is about the size of a sugar cube. And you heard me say that earlier in the video. I said the sugar cube is about the size of a gram. That's because a lot of these things were based on water, and we've defined the density of water to be 1 gram per milliliter. So 1 milliliter of water is about 1 gram of water. So like I said, about the size of a sugar cube is what we're talking about. But more conveniently for us, it's better to think of density expressed in either grams per cubic centimeter or grams per milliliter. And those are exactly equal units. So it doesn't matter if you use either of those, you're expressing density with the same relative size. Grams per liter is used for gases. When we're expressing the density of a gas like air or carbon dioxide, that's useful to use grams per liter. The reason is because gases are very light, so you need a larger volume, like a liter, to get enough grams to make the unit look like it's a number between 1 and 10. So why do we care about density in a chemistry class? Because we talk a lot about gases. Gases are one of the three phases of matter. And so we want to understand the chemical and physical behavior of gases. So density of gases is one thing that is important. Hot gases rise in the air because they're less dense than cooler gases. That's how a hot air balloon works. Talking about liquids, salt water is more dense than fresh water. You can float better in seawater. In the density of an egg lab, you'll make what's called a saturated solution of salt water. The density of salt water is higher than the density of fresh water because, by definition, density is mass per volume. So you can imagine that salt water has, not only does it have water in it, but it has salt, sodium chloride. That's the main. It has other ingredients in it, but sodium chloride is the main salt in ionic compound found in seawater. So you actually have more mass crammed in per unit volume relative to fresh water. So the density of salt water is going to be a little bit larger than fresh water. Here's some densities of common substances just to give you an idea for comparison. Again, regular water is based on our measurement systems, is given a density of 1 gram per cubic centimeter. Ice actually has a density a little bit less than 1. That's why ice floats on a frozen lake or pond. Good for the fish that's true. If ice were more dense than water, lakes would freeze from the bottom up, and that would be bad news for the fish that live in the water. Water is one of the few substances that actually has a density of the solid phase is actually less dense than the liquid phase. Most substances have a solid phase that's more dense than the liquid phase. Dry air has a density of about 1.2 grams per liter. You can see if it's a gas, it's expressed with grams per liter. If it's a liquid or solid, it's usually expressed with grams per cubic centimeter or grams per milliliter. Carbon dioxide, another gas, is 1.8 grams per liter. So it's a little bit denser than dry air. That's why you might have seen in science labs and movies and things when you see carbon dioxide, it actually sinks as it comes out of the flask or the beaker as it's bubbling away. It's denser than air. Helium balloons rise because the density of helium is a lot less than air. Gasoline and hydrocarbons are usually a little bit less dense than water. That's why the oil floats on water. A less dense liquid will always float on a more dense liquid. Gold is very dense, heavy, 19.3. Iron is very dense, 7.9 grams per cubic centimeter. So try to get a feel for the relative densities of objects. That will help you understand the physical properties of things a little bit better. Continuing on, I think I made an error in the last video, not that it is terribly important, but remember I was talking about the base unit of time. I was saying that we base it on this cesium-133 atom, which is a metal, and I said it had to do with the electrons, but actually it has to do with the radiation transition going on of the radiation. So radiation is more of a physical phenomenon, not a chemical phenomenon. But my point is that it's a regularly occurring natural process that never changes. That's why we've chosen to base the second on this speed or the frequency of a radiation transition in a certain atom. So that's very obscure information, I know, but again, the point is that we have to have something, a reference, a standard to base all these different units on that never changes. The next section of the book is dealing with uncertainty, accuracy, and precision. So we want to define those two things. We want to distinguish between exact and uncertain numbers. and represent things in sig figs and rounding rules and things like that. And this is a really important skill to have, is treating numbers properly in chemistry, and then also knowing how to do unit conversion properly. So counting in science, what's different about it? Counting is the only type of measurement that's free from uncertainty. So the reason why we need to use significant figures, significant digits, is because whenever we make a measurement, there's some level of uncertainty. We're not quite sure, or we're just reading our device with the best, highest precision that we can. But there's always a level of uncertainty with that. But counting is not, there's no uncertainty in counting. The result of counting is an exact number. So remember that term, exact number. If I count all of us in this class, I believe there's 23 or 24 of us. So that's a counted number. That has an infinite number of significant figures. There's 24 students in a class, for instance. That's a counted quantity. There's 12 dozen, there's 12 eggs in a dozen. There's no uncertainty with that. We know exactly that a dozen is exactly 12. It's not 11, it's not 13, it's exactly 12. Some of the defined quantities for measurements are also defined as exact. 1 foot is exactly 12 inches. 1 inch is exactly 2.54 centimeters. 1 gram is exactly 0.001 kilograms, and so on. However, quantities derived from measurements other than counting are uncertain. So these numbers are not exact. There's always going to be a limitation of the measuring device. So I want to review that with you here. A measured number must always be reported in a way to indicate its uncertainty. So the general rule that we follow is that when you record a measurement, you're allowed to estimate one uncertain digit. That's it. In the last decimal place, you're allowed to be off by either 1 high or 1 low, plus or minus 1, we say. So for instance, this figure in your textbook, figure 1.26, if you're reading the volume of water in a graduated cylinder. Now, a graduated cylinder looks like this. It's a piece of glassware, and it's just has calibrated or has divisions on it called graduations. This is a 50 mil graduated cylinder, and each one of these little marks corresponds to 1 milliliter. And so you actually have to estimate to the 10th place with this device. So this figure here is similar. In these marks here on this diagram correspond to 1 milliliter, just like they do on here. So what does that mean? How do we use this device properly? Well, if you focus in on the level of water here, notice how the level of water is curved. Water, when it's in a piece of glassware, actually makes a curved surface upward because the water is attracted to the glass, so it pulls itself upward. When you read the level of a liquid, you want to be at eye level. So you want to be right at eye level. Imagine that you're looking here, and here's your eye. You want to be at eye level. You want to be at eye level because you're going to be a little low or a little high, depending on if you're above or below the meniscus. So how would we read this volume properly? We would say V, capital V equals, well, we know it's not 20, and we know it's not 21, and we know it's not 22, but it's somewhere between 21. It's a little bit higher than 21, but it's less than 22. Well, to me, it looks like that level is about 60% of the way between here and there. So I would say that it's 21.6 little m capital L milliliters. These are the certain digits. The 2 and the 1, no matter who reads the flask, we're always going to have 100% of the time, everybody's going to say a 2 and the 1. However, the last decimal place is the uncertain digit. So depending on who you have measure it, they might be off a little bit. Somebody might say, no, I don't think it's 21.6. I think it's a little bit higher than that, 21.7 milliliters. So that's why we say that the last decimal place is usually, you're allowed to estimate one uncertain digit. So plus or minus 1 higher or lower than what most people think. So we generally would express that. We would say then that the volume is equal to 21.6 milliliters plus or minus 0.1 milliliters. That expresses the precision of the measuring device. To measure the volume of liquid in this graduated cylinder, you must mentally subdivide the distance between the 21 and 22 milliliter marks into a tenth of a milliliter, and then make the reading estimate at the bottom of the meniscus. So again, on this device, on this one here, you'd see this would be 20, 21, 22, 23, 24, 25, and so on. But the water level could be in between some of these marks. So how do you express a level that's in between? You have to go to the tenths place. That's how you properly read a device like a graduated cylinder. Let's do a little practice with that just to make sure you're comfortable with that. So if you look at a 10 milliliter graduated cylinder, here's an example of a 10 milliliter graduated cylinder. It has a little bit higher precision. Compare it to this one. You can see, I think you can see in that camera shot, that this one here on the right, every little mark, okay, that's in between the 20 and the 30 or the 30 and the 40, each of those little marks corresponds to 1 milliliter. How do I know that? Because in between 30 and 40, that's 10, and there's 10 little marks, so each one of those is 1 milliliter. But if you look at this one, this 10 milliliter graduated cylinder, because it only can hold 10 from bottom to top, this one has 10 marks in between 1 milliliter. Therefore, the littlest mark on this one is not 1 milliliter, but it's a tenth of a milliliter. So if you can read exactly the tenth of a milliliter, you can actually estimate to the next decimal place, which is the hundredth of a milliliter. That's why this is a magnified view of that graduated cylinder. If you're looking at the water level or the liquid level inside this cylinder, you'd actually get 2 decimal places compared to just 1 with a 50 mil graduated cylinder. So again, make sure, and we'll practice in lab, make sure you can read these devices properly. How did we come up with 6.63 for this one? Well, again, if you look here, you're at eye level, you see that the, actually this is a burette, sorry, we're reading downward. But anyway, it is a precision to 2 decimal places. So again, that's a little confusing. This is called a burette, not a graduated cylinder. How did I know that from looking at that? Because look here, on the graduated cylinder, obviously the numbers increase as you go from bottom to top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, out to the top. This one is increasing downward, and that is not a mistake. This is a burette. So you'll use this in the density of an egg lab. So it's read the same way as the graduated cylinder. It's just you have to read in reverse, so to speak. So notice that the level of the liquid is greater than 6 but less than 7. So it's increasing downward. I can't stress that enough because it's easy to get confused with that. So volume is increasing downward for this burette. So it's 6.1, 6.2, 6.3, 6.4, 6.5, 6.6. It's a little past the 6.6 line, and it's about 1/3 of the way past it. The distance between here and this relative to this is about 1/3. That's where this last place, decimal place of 3 comes from. So again, notice that the this 3 is the uncertain digit. That's the estimate. The last decimal place is an estimate. So somebody else might say it's 6.64, or somebody might say it's 6.62. Who's right? Everybody's right. We're all uncertain. The last decimal place is usually uncertain by 1. The graduated cylinder, again, this would be 40. If you're at eye level, it would be 44, but not quite 45. It's almost to 45, so a reasonable volume would be 44.8 milliliters. How would you use measure a ruler with this simplified ruler? Let's say you had a ruler that was only this precise. How would you do that? Well, this isn't a very good ruler because it only has one mark in between each digit. So actually two marks between each number. So we would say, we don't even know what unit this is, but it would have a measurement of 7.5 about. That's about as precise as we can get. I can't say 7.50, and I can't say 7.49. I can only say 7.1, 7.2, 7.3, something like that. I can get the tenths unit place. That's my uncertain digit on this particular device. So depending on the device you're using, whether it's liquid volume or length or temperature, you have to carefully look at the divisions and how many divisions there are on the device to know how many significant figures to put in your measurement. If you look at a thermometer, for instance, this is a magnified view of a thermometer. This particular thermometer would be, this temperature would be 21.3 degrees C. So this, you can imagine, this is a thermometer. We're reading in degrees Celsius. This one, same precision. It only has 1 degree between for each mark, because there's 10 here and it's divided by 10, so each of these is 1. That would be exactly on the mark. So that would be 22.0 degrees C. Now if you used a thermometer that had graduations that were in between these, so in between each of these there's 10 graduations, you can get more precision with this one. The level of the liquid inside this thermometer is just a little bit beyond this first mark past this one. So this would be read as 22.1, I'll say 2 centimeters. Notice that with this particular thermometer, I'm able to get 2 decimal places, and with these, I was only able to get 1. That's because this one, we say this one is more precise, because it has more divisions in between the between 1 degree Celsius, 20, 21, 22, etc. So that is very important that you can do that.